Okay, welcome to the March Astronomy Club of Akron's membership meeting. Today we're going to have a talk about mirror grinding, if you want to make your own telescope mirror. And Jim, could you hit the slide here? There's a couple things before we get into grinding, because we're going to do some demonstrations. Before we get into grinding, there's a couple of things you need to think about if you want to grind your own telescope mirror. And that is, what objects do you want to look at? Do you want a wide field of view? Do you want to look at comets? Do you want to look at large open clusters? Maybe you want to look at planets. Those viewing objects are going to determine what type of mirror you make, whether it be a 6-inch or an 8-inch, and what is going to be the focal length on the mirror. So when we talk about focal length, we're talking about the distance between the mirror and where the image comes to a focus. If we had a mirror and we're looking at Jupiter, every point of light on Jupiter is hitting every point on the mirror, and if the curve is just right, it's going to bring that image to a focal plane. If we were looking at a star, it would bring it to a focal point. So the focal length is important as to what we want to build into the mirror. A long focal length is going to give us more magnification. A shorter focal length is going to give us less magnification, but you'll get a wider field of view. And we have this parameter called the F number, which is basically just the focal length divided by the objective diameter. And this gives us an idea of how the mirror concentrates light. The lower the F number, the more concentrated that light is. Now, one of the problems we're going to run into when we make a telescope mirror is called spherical aberration. This is the difference between where the center of the mirror focuses light and where the edge of the mirror focuses light. That difference is spherical aberration. Now, we're fortunate that in making a telescope mirror, we don't have to worry about chromatic aberration, which is what you would have to worry about if you were making a lens. And that's really, spherical aberration, we could continue to work on the curve until we work out pretty much all of this spherical aberration. But chromatic aberration is really a law of physics. It's not something it's easy to deal with. With a lens, when light goes through a lens, different wavelengths of light bend at different angles. So they all come to a different focal point. So what lens makers do is they'll have multiple lenses that try to recollect this light so it all comes as close to a point as possible. We don't have to worry about that. That's the good thing, because the light is not traveling through the glass. It's only reflecting off the surface of the glass. We only need to make this part of the mirror perfect. The rest of it, we're not worried. We could have bubbles inside here, and if they're not too large and not too close together, it's not really going to affect us anyway. So we have two of these figures, the sphere and the paraboloid. We could have no spherical aberration. So the paraboloid has no spherical aberration when the object is at infinity, very distant, very parallel rays when they come in. And the sphere doesn't have any spherical aberration when the object is at the center of radius. You could think of this, if this was a curved surface here, you could think of it as a big sphere. And the center of that point to the mirror would be the radius. And that's what, if there was an object at that center, then we would have no spherical aberration if this was a perfect spherical surface. And here's just what a paraboloid looks like. And then we have a paraboloid and a sphere. So basically our process is going to be to make a spherical surface as perfect as we can, and then convert that into a paraboloid. Now, first thing we want to do is take a look at our blanks before we start grinding, and we want to inspect them to see if there's any mirrors. Typically, you're going to get two blanks. These are 8-inch blanks. So one is going to be the mirror, and the other one's going to be the tool. And at the start, it doesn't matter which one you choose to be the mirror and which one you choose to be the tool, but you want to inspect them and make sure that there's no bubbles in there that are going to cause you any problems. If there's a bubble near the surface, then you may want to use that as the tool instead of the mirror, because we don't want, when you grind into it, we don't want to be opening up that bubble and have an imperfection on the surface. If we do, you could always use some black paint after you luminize it, but try to stay away from it if we can. Now, the other issue I see with these blanks is this is a sharp edge here. So that's going to be a problem when you're grinding, because it's going to become even sharper. So what you need to do before you start is you need to put a bevel on this edge. And if you have a oil stone, let's see, I think I have one here. Well, just take an oil stone and just bevel that edge at a 45-degree angle. And you may need to inspect it as you're grinding to make sure that that edge isn't getting sharp. If it gets sharp, it could chip, and if it gets between the mirror and the tool, you're going to have scratches all over your mirror. So you'll have to start over again. There's really no problem that you could get yourself into that you can't get out of. Okay, like John Dobson says, there's no mistake you can make pushing glass that's followed by a life of sorrow. But there are a lot of mistakes that could cost you a lot of time, and that's one of them. So you want to make sure you do a good inspection, and if you don't have a beveled edge, you need to put a beveled edge on there. Now, the process that we're going to be using, basically we're going to be taking these two blanks. We take one is going to be our tool, the other is going to be the mirror, and we're going to be rubbing these one over top the other. We're going to have grinding grits and water in between, and the mirror is going to be on the top, and the tool is going to be on the bottom. And initially, we're going to do what's called rough grinding. We're going to cut out that curve. We're going to be hanging over the side where the center of the mirror is wearing away the edge of the tool. Okay? As we get into finer and finer grits, we're going to be doing more of a face-over-face straight stroke and a reduction in amplitude of the stroke. And so when you're hanging over, this is called a tangent stroke, and then the radial stroke is what we use when we get into finer, fine grinding. But the amplitude would be less. It's what we would call, when we're into fine grinding, we're going to do like a third stroke. That means if you have a 6-inch mirror, a third of 6 would be 2 inches. So the total displacement of the mirror would be 2 inches. You would have it go over 1 inch on one side and then over the other inch on the other side. So a very short amplitude stroke. And I think
question?
Sure.
Just for perspective of this, how, like in a blank that size, how much depth of glass total are we going to be taking off?
Well, it depends on what the F number is. Okay. Now this particular one, this is one that I've been grinding for a little bit. I went through 60 grit and now I'm into 80 grit. The depth of it is going to be about 3/16 of an inch. It's going to be an F3 mirror, that's really fast, and it's really hard to correct. most of the time, mirrors are gonna range from f4 could be up to f15. If you're looking at planets, you need more magnification, so you're gonna be somewhere between f10 and f15. This particular one I wanted to make to try to see open clusters, like the Pleiades or the Beehive, or it'd be good for comets. It's a large aperture, so it'll bring a lot of light in, and comets are faint, so, but it's also going to give us a wide field because it's a very short focal length. So, and that's one of the things that you'll be doing is checking that depth as you go through, because ideally what you want to have is that you get to the right depth the same time that you get to the edge of the mirror. Okay, and right here, I still have about probably an eighth of an inch, maybe 3/16 of an inch from the edge yet. So you want to get to the right depth at the same time that you get to the edge of the mirror. If you don't, let's say you get to your depth, but you're not to the edge of the mirror, now you're going to be too deep. So what we would do in that case is we would take the mirror and put the mirror on the bottom, and then we would put the tool on top. And this will flatten out the curve. Okay. So, and I may need to do this because this is F3, which would be 24 inches. Right now I'm about 22.5 inches. So that's a little bit short. And the thing is, once you get so short, if you want just a standard diagonal in there, you're not going to have enough room to get outside the light path, the light coming in. So, and you know, different eyepieces have barrels, so there, you know, that barrel would actually be on the way. So I'd have to, you know, some eyepieces you might be able to use that don't have that issue, but might have to take this and put the mirror on the bottom and the tool on the top. Now, when you're grinding, you want to make sure that your hands are across the center like this. You want the pressure to be acting as it's like on the center. You don't want your hands up here. You don't want your hands over here. You want them right across, and you're going to be pushing the glass back and forth. Now, let's see if we can get some. Just going to wet these up a little bit. And I'll put some, this is 80 grit, pretty coarse grit, and I do have all the different grits out there if you want to take a look at that. And you just kind of sprinkle.
What is that, Ron? What is it made out of?
This one is carborundum. This is silicon carbide. You could also, they also make aluminum oxide grit, but this is carborundum. So when you put the mirror down, even in rough grinding, get used to putting the mirror down like this and not like this. Okay, you don't want to take anything off this edge, especially when you're in fine grinding, because what's going to happen is you're going to get a turned edge. Okay, so you get always in the habit of putting the mirror down like this. It's very important that you don't get a turned edge, all right, because this is a very large amount of area here. If you take some of this off the edge, you got a large area. If you have a little bit in the center, it's not so bad. But if you have a large area over here, even a small area, but it's all the way around the circumference, it turns out to be a large area. So you have to be very careful, especially in fine grinding, but just get into the habit of putting the mirror down like that. Now, in this particular case, I'm using a 7-inch tool. This is actually a reactor sight glass, but it turns out reactor sight glasses are made of the same material as telescope mirrors, borosilicate glass. So it turns out to be the right size I wanted. I didn't want to use the same size blank because it's hard to get down to an F3. If you use two of the same, which most of the time you will, you could easily get down to F4, and then of course going any higher is no problem. When you want to make the depth more, you just hang over the side more. And if you want to, if you don't want the depth that deep, then just stay with short strokes back and forth. But right now we're still in the rough grinding. 80 grit is still pretty rough grit. So yeah, so I just kind of move this around a little bit, and then we're just now the thing you want to keep in mind is that you want to continually be turning the mirror. Every so often you want to turn the tool, but it's very important that you continue to turn the mirror. So you have you're constantly touching all the parts of the tool. Every so often you need to turn the tool, but constantly be turning the mirror. Any defect on the tool is not going to be transmitted to the mirror as long as you keep turning the mirror. So we're now, and again, when you're taking it off, not a huge deal in rough grinding, but just get into the habit of putting a little bit of twist and pull it back so you don't scrape that edge. So you lift it off like that. Now, I could keep going with that, but that's basically the rough grinding part. And then what you would do is just wash it up and then recharge it again.
Have you already pretty much ground down that
It's pretty close.
powder that you need to replace it?
It's pretty close. The only thing is I'm not out to the edge yet, and I don't want to go too much deeper. So probably what I'm going to do is put the mirror on the bottom and the tool on the top to flatten out the mirror to get out to the edge.
Sorry, what I meant to say was your borosilicate material, or the carburet, whatever you call it.
Oh, carborundum?
Yeah. How long?
Silicon carbide?
How long can you use that before you pulverized it and it's no longer giving you that coarse?
I probably could have went about twice as long as I did.
Okay.
The finer and finer grits that you get, the longer you could go. If that was 60 grit, that's probably all I would have been able to go. You can't go that long because it's cutting into the glass, but it's also breaking down very fast.
Right. Like sandpaper does.
Yes. It's basically the same thing as what's on sandpaper. But the silicon carbide, or silicon carbide carborundum, is much better than aluminum oxide. A lot of times on sandpaper they have aluminum oxide. So now let me show you a couple different ways of measuring the what's called the sagitta, the sag. Could you see that? Could you see a gap through there? Could you see that?
Yeah.
That's a pretty good size. Let's see right there. It's a pretty good size gap. So one way of doing that, and there's a formula I'll show you, but there's another way that you could measure what that depth is, or really what you're more interested in is what is the focal length. So here, this is a mirror rack, all right, and I have a mirror, and this turns out to be an aluminum mirror. We're going to use this for fine grinding. Wow. But what I could do is bring it over here. What I could do is I could spray that with water, and we could read the curve off read the focal length off the water curve. So let me spray that a little bit. And then what I'm going to do, I'll just turn it around so you could see what I'm trying to do. I'll take this white piece of paper here, and I got a flashlight, and let me see if I could, so you see that image there? So I just bring that into focus, and So it's right about there. I would just measure that distance. Now that distance is going to be the radius of the sphere, and the focal length is half of that. So half of that length would have been the focal length. And that's an easy way to do it. The other way you could do it is, if you don't feel like wetting the curve and using that mirror rack, is you simply just measure that distance between your straight edge and the mirror. And you could do that. What I do is I'll put some change in there, maybe 2, 3 dimes or 2 dimes, depending on what it is, and just get it on the corner and see when it starts to slide under, just the edge of it when it starts to go under. And then you can get a pretty good idea of what that focal length is for there. I'll show you the formula once we continue in here, but let me show you right here. This is, can we flip back?
Do you polish those aluminum mirrors basically the same way you polish the glass mirrors?
Yes, it gets a little bit trickier when you get into the finer grits, because you get really smooth surfaces with metal. They want to have cohesion, so it's a little trickier, but basically the same.
And you'll have a tool and a mirror, and it's both metal, and
Yeah, this is
same deal.
This is my tool,
Ah, okay.
and you notice I cut it down. I started with a 6-inch disc, but I could not get anywhere close to F2, so I cut 1 inch off this and used it as the tool. And I'm at F2.1. So yeah, you just have, now for the most part, people aren't going to be making F2 mirrors and F3 mirrors. You're going to be making it between F4 and F10 or F12, and then you could start with 2 identical blanks like this. This is how normally you would start, 2 identical blanks. So here, this is my setup at home, and what I have is, you notice this sink here, so I have a water source. So it's just easy within stepping distance. I could wash all the grits off, all the used grits off, and then recharge it, and then go for another wet. Each of these are called wets. So depending on how deep you're going, it's going to depend on how many wets you use. Now, here's a close-up. This needs to be really solidly bolted into the wall so it doesn't move. And between each sets of grits, you have to clean up, absolutely pristine. Do a very good cleanup job, because you don't want to carry over grits. When you change your clothes, you don't want to have any grits in your hair, so that's going to get onto the mirror, because you'll just have to start over again. So you want to clean this up very clean before you go on to the next set. And here is that formula. So you have the focal length is equal to r squared divided by the sag times 1/4. So r is going to be the radius of the mirror. So if you like doing math, that's a way to do it without having to set up the mirror in the mirror rack. You simply measure it, or you know your focal length, so you can calculate out how deep that needs to be, and then you keep measuring it until you're at that depth. But again, you want to get to that depth at the same time that the mirror gets out to the edge, or else you're going to have to put the mirror on the bottom and flatten it out with the tool.
When you have your mirror mounted, though, you're not actually, or I don't think you typically are using the entire diameter. Aren't you using like a little bit in from whatever hardware is holding the mirror in place?
No, the hardware that holds the mirror in place is on the side. You're using a full face of the
Nothing
mirror.
that goes over the edge on the side?
Yes, most of them it's on the side. It's being
Okay.
held like that, and then it's supported in the back with 3 points, spring-loaded, that you could adjust it and tilt it. But no, you're right. Some of the smaller ones, some of the smaller mirrors do have a tab, so you have 3 tabs.
Yeah.
But larger
I
mirrors,
guess that's my question then,
Yeah.
is the diameter then really just inside the tab? Or do you still count the whole
No, the whole
thing
diameter,
and
the whole
you just know
diameter,
that you've got?
that tab really doesn't make a difference.
Okay,
But, larger mirrors, I've seen them held like with straps. You have like maybe a stainless steel strap
okay.
that holds that. It's not anything touching the mirror. They're heavy, you can't, the smaller ones, I guess you can get away with that, and they're not as critical on people using small mirrors, but the larger ones, they're held from the side and then supported from the back. So here's another formula here, but this R is the radius of the sphere. So not so helpful unless you remember that the radius of the sphere is equal to 2 times the focal length. So you could just substitute in that for the large R, and then you would be able to find out what the sig eta is. So here's another way to measure the focal length. And this is a direct measurement where we're measuring the radius of the sphere with this flashlight test that I just did. When you do this, since the rays are parallel, you're going to be measuring the actual focal length. So you just catch the sun and you just move it back and forth until you form a crisp image under the eve, and then just measure that distance, and that'll give you a direct measurement of the focal length. But of course, you have to have the sun out if you want to do that.
Why does it say the mirror has to be wet?
I'm sorry?
Why is the mirror wet?
Well, when you're doing fine grinding, even in rough grinding and fine grinding, it doesn't reflect any light.
Oh,
So now this one is is ground up to 40. So I could see an image, but I have to look like at a 45-degree angle. I could see an image. Okay, I could see the light there, but looking directly on, I can't see an image. Or if you're looking like that, you might be able to see an image. But if you put the water curve that fills in all that roughness,
okay.
and you could read off the water curve. So here, this is this mirror. I took a picture of it, and you see right here, this is the beveled edge. Okay, let me get this next one does. This is the beveled edge right here. All right, and this is where we ground out to. We still have to come this distance. And so, like I said, I'm at 22.5, so probably what's going to happen is I'm going to end up putting the mirror on the bottom to get out to the edge without decreasing the focal length. Actually, it'll increase the focal length, which would be a good thing. Now, here is the grinding schedule, or this is one grinding schedule. I use something a little bit different. I follow what John Dobson does. He does 60 grit. He starts out with 60 instead of 80. It's a much coarser grit. It grinds much faster, but you lose a lot of material. And then he goes to 80, followed by 100, 120, followed by 80, 100, and then 240, 400, and 1,000. And I have those grits set up over there if you want to see what those grinding grits look like.
That bottom one said 305.
Oh, 305. Well, this is iron oxide material, and that's used for in place of 1,000, but it's also used for polishing. So the procedure is going to be first to do rough grinding to form that curve, and then you use finer and finer grits to make it closer and closer to a sphere.
Yeah, I just wondered why it's in the 300s and not 1,000 like you just said.
Well, because it's a totally different material.
Okay.
This is going to be either aluminum oxide or carborundum. This is iron oxide. This is equivalent to what this material is here. This is cerium oxide. Okay, so this is the polishing agent that we use. Now we're not going to use this we're not going to put this between the two mirrors. We're going to use a pitch lap like this to be able to polish.
Okay.
When we are doing grinding, we're cutting the glass with the grit. When we do polishing, we're not cutting the glass anymore. We're using the pitch lap to just take layers off the glass.
Do you get on your first rough grind, do you get the general shape of your mirror at that point? Will it edge to edge and center to center? Is that complete as far as that goes?
It's pretty close. The focal length is going to change a few inches, couple inches,
Right.
as you get into the finer grinding.
Got it.
But and you can put the mirror on the bottom for some to kind of keep it the same. But yeah, after rough grinding, you basically have your curve. You're not going to change it that much by going into fine grinding. And here's another setup where he's measuring. This is similar to what we did here. He's got a light source, and then he's got his mirror, and he's got this screen right here, and he's just bringing the mirror back and forth. He catches the light source, and he's bringing the mirror back and forth until he gets a sharp image. It's another way of measuring the focal length. Now, of course, this would be measuring the radius, so you would divide this by 2 to get the actual focal length. And this is how you would have your setup, because what we're going to do, once we get a spherical mirror, we're going to need to test it. Well, at least when we're done with fine grinding, we're going to polish it, and we're going to polish it into as close to a sphere as we can. And we need to test that mirror to know how close we are to a sphere. So we take it and polish it to a sphere, and once we have absolutely no spherical aberration, in other words, when you're measuring at the center of radius, center of that sphere, you have no spherical aberration. Once we get to that point, then we add spherical aberration into it. We parabolize the mirror, and we add, but we know how much we want to add. It's a little bit of a trick to that, to do that, but we know what we want to add into the mirror, how much spherical aberration we want to add into, have a perfect focus for infinity. So here's the center of curvature of the mirror, and then the focal length is half of that. Now, once we go through fine grinding, and Jim, let's go back to the camera. Let's do some fine grinding over here. Here's the tool. Just gonna wash my hands a little bit so I don't take any grits over. Try to bring this over. I'm just going to sprinkle some of this 400 grit on there. And what I like to do is I just like to move this around a little bit, just get it over the full face. And then we place it on, and you see it's on the water curve. We got to press that water out. And then we just very slow motions, or very slow, small amplitude on the stroke. Continually turning the mirror. Every once in a while, turn the tool. And these wets could go 5 to 10 minutes. And you'll hear it. you'll hear a little growling of the glass, or in this case, the metal.
What's the growl?
Well, the growling is the grit biting into the glass. I mean, it's easy to...
Does it change, where you can hear it or feel it?
Oh, yes, yeah, from grit to grit. I mean, you could definitely hear it when you're doing the rough
right
grinding.
now with this grit right here, can you tell the beginning to the end, is there a change in how it feels?
Not so much.
Not so much?
No, not, you're saying just with the 400?
Yeah.
Not so much. You know you're getting near the end of the wet when it starts sticking. So if it starts to stick, don't push it over, just back off and then take it off wet, clean the old grit off, the wasted grit, and then recharge it. Yeah, I can hear it. It's growling, which is good. That's it's taking the material off. And then when you're taking it off, you want to try to rotate this thing back so you keep the edge from touching. Now you might have to slide it off a little bit because they're sticking together, and then let it pop. And then you just wash the face and the tool, and then you just recharge it and do it again. So the next step, when we go through all the grits, we go through 60, 80, 100, 240, 400, and 1,000. The next step is to polish the mirror, bring it into a sphere. And we do that with a pitch lap. And I'm sorry that I only have this smaller pitch lap. I had larger ones, but I ended up, they were so old, I just heated up and threw the pitch out. Pitch lap is, you want to waffle it like this, and I recommend, again, this is something you want to be careful when you're buying the stuff. I ran into a lot of different issues that made me start over again. One was I bought, the first pitch that I bought was contaminated. So I went through that whole process with the 12.5-inch mirror, and then I poured my pitch lap, and when I started polishing, I just put scrapes in it because it was contaminated. So this is one of the pitches I found are very good.
Move that over a little bit because we couldn't see it very well.
Okay. Google's, this is made by Universal Photonics. Actually, I believe it's imported from the Swiss, but they package it and distribute it. This is very good pitch. This is a medium soft pitch, and it works very well. The way you would pour the pitch lap is you could heat this in your oven. You could heat it right in the can. Now this melts about 160 degrees. So you wanna heat this slow. If you heat it too fast, it loses its ability to yield. And that's what you want it to do when you're polishing. You want these squares to yield as they go over the mirror. So they plane the surface of the glass and just take off layers of it. So,
What are the squares for?
I'm sorry?
Why the
Why the
squares?
waffle pattern?
Yeah.
Well, because each of these individual squares have to have a place to move to. They're yielding. If it was one solid piece, then it's not going to be able to yield as easy. So each of these individual squares, they're deforming, is what I'm saying. They have to have room to deform into. And it's that yielding that's doing the polishing on the mirror. Again, we're not cutting into the glass. We're just layering, we're taking off layers by planing the glass. So to pour your pitch lap, first you need to melt this. Yes, sir?
If it weren't for the waffle, wouldn't the mirror maybe stick to the tool? I mean, well,
Uh,
it might.
It,
very sticky
no,
then.
no, you could, if you had it solid, you'd still be able to push it back and forth. Although you bring up a good point, which I'll mention about, John Dobson likes to, what he calls marry the tool, or marry the mirror and the pitch. He likes to have them together, you know, so they keep the same surface. If you use a soft pitch like this, and you get any heat in your house, they will stick together, and you will not be able to get them apart. I mean, there's only two ways I know of that you can get them apart. You could put a stick of dynamite underneath it, but problem with that is you won't have your tool and your pitch lap to work with. The other way you can get them apart, which is the way I use to get them apart, is I put it in the oven and slowly heat it. The problem is it heats from the outside in. So the outside runs out and it makes a real mess in your oven. Even if you have it covered with aluminum foil, it just runs, and while the inside is still cool, so it's really a mess. And then you try to pull them apart and it's like, you know, molasses, you know, just running and sticking. So it makes a real mess. So I do not marry the tool or the mirror and the pitch lap. What I do is I do a hot press before I start polishing. So I'll dunk this in hot water, get it soft, and then I'll press it against the mirror with cerium oxide and water on here. And I'll just press it against the mirror so I get the curve of the mirror on the pitch lap. And then do that several times, and then I'll start polishing.
But you
So
also cut the waffle pattern into it?
Yeah, what happens, first we have this in the oven, we heat this up, we get this to a liquid form, and then we want to pour the pitch lap. Now when we're pouring a pitch lap, let's say we were pouring on this 8-inch blank, sometimes I find it nice to make a cardboard ring around here so the pitch doesn't run off. You could do that. You could take your chances and just pour it on there. What you want to have on the tool, most of the time you'll be using your tool, but you don't have to. You could use just a regular blank. You want to put turpentine on the pitch lap surface, okay? So the pitch does stick to the glass. And after you get the pitch on there and you waffle it, then you're going to take your mirror with cerium oxide and water on it so it doesn't stick, and then you're going to press it onto the pitch to get the pitch lap to the curve of the mirror. So first, like I said, you could have a cardboard ring around there. You have this melted in your oven. It might take 3-4 hours to melt this. You have to melt it slow. And then you put some turpentine on the surface, and then you pour your pitch, and then as it's still hot, you want to take a stick that's wet, soaking wet, and then you just waffle it about every inch. Just waffle it one way, back the other, press down hard, and then you take your mirror, cerium oxide on it and water, place it on and press it down and pull it off. Those channels are going to fill in, so you got to open them up again. You press it down again and just let it sit there for about 10 or 15 minutes, and then separate it. I would keep them separated. Dobson says let them dry up until they're dry, and then you can marry the mirror and the pitch lap. But I tried that once and I'll never try it again because it just made such a mess. So I always do a hot press before I start polishing. That's the easy way. So now when you polish, you're going to want to use, and it's best to, you might want to have different pitch lap sizes. I would like to polish with a full face. All right, so I would like to make a pitch lap the same size as my mirror. and you want to do short strokes. You could, no more than a third amplitude. So if you have a 6-inch mirror, you don't want to move, you don't want to go any more than, for a 6-inch mirror, you don't want to move any more than 1 inch off the edge either way. You're going to have a total displacement of 2 inches. So no more than a third stroke. And you could do a zigzag, or you could use just a straight radial stroke. And you're going to want to polish, if you can, try to polish.
I'm sorry
for,
to keep interrupting you. I'm getting you with this one, but you're in the way of that one. So if you want to move that one, we should do it now. Or if the front view is fine, then that's,
oh, okay.
it's, yeah. Okay, yeah, that might be better.
Now-
Yes,
now I
perfect,
see it,
good.
yeah.
So when you're polishing, you want to try to do sessions of about 30 minutes. You need to build some heat up in the pitch lap. So these squares, again, so they yield under pressure. Get some heat, and you'll start polishing. Now you'll notice initially it looks like you're getting a lot of ground, making a lot of ground. It's kind of a superficial polish. You take your mirror and just look at it from the side, and you'll notice that the outside is hazy. Okay, so you want to continue to polish until you is polished all the way out to the edge. And hopefully, if you are very careful in fine grinding, it will polish all the way out to the edge. Now, you may find out that you're polishing and it never gets out to the edge. That's because you have basically you have a turned edge. It's not really turned down so much as it is just flat. Let me just. Turn those phones off. So that's all in fine grinding. If you were very careful taking your mirror off and putting it on, you won't have a turned edge. But if you have a turned edge, then it depends on how bad it is. A parabolic mirror does have a turned edge. So if you are making a spherical mirror and you stop there and you have a little bit of a turned edge, if it's within tolerance of a parabolic mirror, then you actually have a better mirror than a perfect sphere. If it's outside that tolerance and you can go back and polish more and take that turned edge off, that's great. The worst kind is when no matter how much polishing you do, you can't get the turned edge out of there, and that's because you made an issue in fine grinding, where you were touching that edge against the tool glass. All right, so what we want to do is we want to polish this until we have a perfect sphere. And Jim, if we can go back to the video or to the presentation. Jim, can we go back to the presentation? Okay, so here is testing your mirror, and you want to test it to see if you have a sphere. You're probably somewhat spherical, but probably not perfectly spherical. And this is a test rig. This one is called a knife edge micrometer. It has this dial on the back, which we can move this table. We basically have a table that's on a 1/2 inch pipe, and by rotating this knob, we could push the table forward and backward. We're going to use that to test our spherical aberration in our parabolic mirror. We also have this knife edge here, and we have a slit. So what we're going to do is we're going to take this slit out, and we have this is called a lighthouse. It's got a 7-watt bulb inside there, and we're going to shoot the image of the bulb onto the mirror. Okay, and then the mirror is going to reflect it back, and we want to try to bring that image right here. Once we find it, then what we do is we put the slit in. Now this slit is about 20 thousandths separation between two razor blades. Once we have it lined up, then we bring this knife edge in, and then we have a drive here, so we're able to drive the knife into the image of the mirror. You're going to see the whole mirror is going to be lit up, but it's that slit that we're looking at, and you could drive it in. You also have this adjustment so you can make the knife parallel with the slit. Drive that back, and then this is a 1/4-20 bolt in here, so one rotation is 50 thousandths. So we're going to use that to measure our spherical aberration in the mirror when we parabolize. We're not at that point yet, but that's what this is for. This is good for testing a mirror to a sphere, but it's also good for parabolizing the mirror. So we use that. You don't need such a fancy setup, but that's how that's going to work. Now, here's our lighthouse here. We have our slit, and then when we bring, what we want to do is we want to try to find the center of radius, okay, of that sphere. So we drive the knife edge in, and if we're inside of focus, we're going to start to hit these rays here, and what's going to happen is we're going to see the left side of the mirror darken. Right in this area, these are diffraction rates right here. But we're going to see, if we're inside focus, we're going to see as you drive the knife in, this is going to darken. If we're outside of focus, if the knife is outside of focus, then the right side is going to darken as we drive the knife in. So now we know you're either inside focus or outside focus. You want to try to get that knife at focus. When your mirror is a perfect sphere and you drive your knife in at focus, what's going to happen is it's just going to gray, and it's going to gray all at once. And then you know when that happens, you know that you have a perfect sphere. That's not going to happen as soon as your first time polishing. You're going to have some type of defect. Now here is an area on the mirror where, you know, all of this section in here is focusing at the same focal length. But this area in here is focusing right here. This is the defect of this area in here. Okay. So we need to, in this case, we need to continue to polish until we get the whole thing graying at once. If we would bring the knife in at this point, we could gray this area. We would be able to gray this area, but then this area here would be dark on the left side and light on the other side, because if we brought that in, this would be, we would be inside of focus. So you're going to see when you drive the knife in, you could gray this section, but then this section in here is going to show that you're out. It's outside of the knife is inside focus. Now you can think of this, the image you get here, you could think of it like a light bulb on the side that just at a grazing angle, kind of like the surface of the moon when you're looking at craters on the Terminator. The sunlight is at a very grazing angle. If you have a crater, what happens is the one part is in darkness and then the other part is lit up. It's kind of the same way you have here. So here, this would be showing us that we have a a hole in the center of the mirror. Okay, it's a low spot. It's an area of shorter focal length. If this area was bright and this area was dark, then we would have a hill in the center, which is not so much a hill, it's more of just a flat area that has a longer focal length. When you have, most of the time when you have those type of issues, it's best just to go back to the polishing table and continue to polish until you end up with a nice perfect sphere. Okay, so when you cut in at focus, the entire mirror goes gray all at once. Then you know you have a perfect sphere, or near a perfect sphere. And at that point, then you could start to parabolize. Now here's a couple problems you might run into. We talked about this when you have the hole. And basically what you have is this area of shorter radius or shorter focal length. And so they're showing the work line right here. You know, that may look pretty easy, but it's not the easiest. You're more likely to make it worse than better. It's easier just to continue to polish, and that'll all work out by its own. It'll all come out in the wash, so to speak. Here is a hill, and you see it's just an area that is a flatter area in the center. You might be able to work that out if you had a smaller pitch lap like this. Okay, so if you had let's say a 10-inch, 8-inch or 10-inch, if you used a smaller pitch lap, then you could work that center and leave the outside edges alone. It's harder to do if you have a full-size pitch lap. That's why sometimes it's best to have multiple pitch laps, because then you could do some of this work. But you'll always be able to get out of it if you have the full-size pitch lap. Just continue to do more polishing, and that'll work out. Now here you have a turned edge, and this, you know, it's like the good, the bad, and the ugly. The good is if it's within tolerance of a parabolic curve, it's not too bad. It's actually a better spherical mirror than just a sphere itself. If it's bad, you might be able to polish it out with more polishing. And if it's the ugly would be that no matter how much polishing you do, you can't get the turned edge off. You've got to go back into fine grinding to resurface the mirror. Here's an oblate spheroid. Just more polishing on that. Now here's a good test on a turned edge. When you push the knife into the focal plane, you'll see the mirror gray, but if you have a bright edge on this side and a dark edge on this side, you're gonna have a turned edge. What you should have is this side should be brighter. The right side's always going to be brighter. You're always going to have a diffraction ring here. The right side will be brighter, and you'll have the left side will be bright, but not as bright as the right. So that's a good edge. Here's this test I like, because when you turn the knife in, you're going to see this ear come up like this on both sides here, kind of crawls up there, and that's a indication of a turned edge. And you put the knife 1 inch inside the focus, and then you cut it in, and you'll see this. This one uses a straight edge. I'm not crazy about this one. Now for parabolizing, once you get the spherical surface, then you want to parabolize it. And you do that with a long stroke. So if you have your full pitch lap, that's the best way to do it. At this point, from polishing, your pitch lap is probably hard as a rock. So unless it deforms and yields, it's not going to parabolize the mirror. So you may want to pour a new pitch lap just for parabolizing. And you may want to have a smaller one if you want to touch it up. But it's probably worth it to have a new pitch lap just for parabolizing, and that's the nice thing about this. This is a softer pitch where it will deform easily. It's good for parabolizing. So you work with this zigzag motion here. Okay, you go back and forth, and you want to have it so the center is not going past, for a 6-inch mirror, not past 3/4 of an inch. So you could put a tape on the center so you could see how you're zigzagging through here. Now this is your normal stroke, and that's a long stroke. It's beyond a third amplitude stroke. These areas in here, you see what they're doing. They're concentrating in the center. All right. So they're wearing the edge, and on here they're concentrating on the outsides where they're wearing the center. Remember, the pitch lap is on the bottom, the mirror is on the top, so the mirror is going to be out here. You're concentrating on the center. And the same with this, when you're on top here, you're wearing the edge. Now, to test it, you make up a mask for the mirror. And I have some masks here. You would put a mask like this, and this is a mask for the 12.5 inch. And what you do is first you find the focus of the center. So you would look at the center and see where that area grays. And when it grays all at once, then you're in focus for the center, and that's going to be your 0 point. Then you look, you're going to have to, this is what you would use again. You would drive your knife back, okay, and then you're going to see where do you have for your 70%. Well, actually, you'd be working on this mask I have. You got the center and you have the edge, so we would work on the edge next in this section here. What you want to do when you drive your knife in, you want to see that these two sections gray at the same time, okay? And it might take a little bit of practice to be able to get them so they gray at the same time. When they gray at the same time, then you know that is the focal length of that area, and then you mark that down on what your reading was on the wheel. And then you do the 70% section. So you change your mask out, and you have for 70%, and then what you try to do is you gray these two areas exactly at the same time, and the shadow goes across. And then you have your 3 readings, and then you could mark them down. In this situation, he has a table, and what he's just marking them down on a piece of paper here. You have your 3 readings. You got your 0 reading, then you got your edge reading, and then you got your 70% zone. And you could use this formula to figure out where you should be. In other words, for the 6-inch mirror, you got, for the 70% zone, it should be 45 thousandths in back of the 0 point, which is where the center of the mirror focuses. And then for the edge zone, it should be 75 thousandths back from the center 0 point. And it's just this formula here. The correction is equal to r squared over large R, which is the radius of the sphere. R squared is going to be the average distance, basically the center of this, the radius from the center to the center of this section here is going to be little r. And you calculate out what your correction should be. So you're definitely not going to get it on the first try. You might have to, you're going to do probably several tries, and may have to go back to a sphere depending on what your mirror looks like. You might make a hole in the center of the mirror, go back, polish it back to a sphere, and then try again with parabolizing it. And the faces of the parabola, these are common faces. This is with the mask off. At the 70% zone, this is what it should look like. And this is what the edge zone should look like. And at the center. And then I just got, John Dobson, of course, he's not living anymore, but he did a lot with teaching people about mirror grinding and telescope building. I know a lot of you know about him. And the Dobsonian telescope is really his design. It's for basically the layman to build his own telescope, and at a relatively cheap price. Unfortunately, right now I learned that the prices of the blanks have gone up dramatically. I had a salesman must have saw our website, and he sent me an email, and I asked him to send me a price sheet, and the prices have gone up dramatically. The 6-inch blank I bought back in '93 was $15, and now it's selling for $75. And the 8-inch, this was $31. Now it's selling for like $305. And that 12.5-inch blank was $132. Now it's $830. And these are all Pyrex. Right now you can't, Pyrex, Corning, who makes Pyrex, doesn't sell commercially. So they stopped, from my understanding, they don't sell commercially, they sell industrial. So what's happening is the other manufacturers are trying to imitate Pyrex, my understanding, because it's proprietary, so you don't know the process and what's in it. But the prices of the blanks have gone up. Even this pitch, when I bought this in probably 90, somewhere between 93 and 95, this was $13 for a kilogram. Right now it's $53. So it's really making the amateur telescope maker, putting them out of business. Because if you're going to spend, you really need 2 of these, so that would be, you're looking at $600 here, another $50 here, and that doesn't even take into account all the wood and everything for making a telescope. Really putting the amateur telescope maker out of business, because you can go and buy an 8-inch Dobsonian for $400. So why, unless you like making things, which I kind of do, so you can take some, get some fun out of that. But the price of this stuff is really astronomical. So anyway, are there any questions? That's basically what I have for the presentation.
Where did your formulas come from? You had all the formulas.
Oh, Edmund Scientific.
Just old, 100 years old, some of that stuff I assume.
Yeah, they're from optics. Yeah, Edmund Scientific, they used to, probably still do, but they used to sell a lot of good books on optics, telescope making, and lenses, and all kind of stuff. I love their Mag 5, which they don't sell anymore, but the Mag 5 Star Atlas, just a perfect star atlas, because whatever you see in the sky is exactly what's on the star map. A lot of star atlases are Mag 6 or Mag 7. You got a lot of stars there, and it's hard to distinguish, sometimes, hard to distinguish what stars you're seeing in the sky based on what's on the chart. But when you look at a Mag 5 is the limit of the naked eye. So what you see on the chart is what you see in the sky. But they don't make that one anymore. I'm not so sure about the other books, but they had a lot of literature they put out in the 60s and 70s, and a lot of it was still continuing up until about 2000. But the problem with the Star Atlas is that it becomes obsolete in about 40 years because of the precession of the axis of the Earth. So the star charts aren't exactly, it's not exactly the same. The coordinates and stuff are different. So Star Atlases, I could see them not making that anymore, although they did for quite a long time. But the other materials probably are still available.
Does that mean your planetarium's a little bit off
Yeah.
from when it's been built, from precession?
No, not really, because we could change the tilt. we could change everything.
So it's an error, precession causes the whole sky to not move in relation to each other.
Yeah, the proper motion of the stars is still negligible, but
Yeah.
yeah, the precession the planetarium can adjust for, but a printed chart is just gonna be wrong.
Yeah,
Precession is the axis of the Earth has a wobble to it about 27,000
okay,
years.
so that makes the whole sky.
So 13,000 years ago, the North Star was Vega,
Yeah,
not Polaris.
yeah.
But if we wanted to, we could adjust for that in the planetarium. Yes.
So, 50 years ago, whenever John was partner on stuff, he used to do parties in his backyard to grind mirrors. How long did it take them to grind mirrors?
I'm not sure, but he worked on it. You know, he went through the whole process fairly quickly.
Cause my dad's half brother did one at his house.
Oh, he
So,
did?
Yeah.
You know, he is an amazing man. He put out a video on mirror grinding and telescope making, and he actually put his phone number on the cassette. I ended up calling him, I just wanted to see if, really, come on, you're gonna talk to John Dobson? Yeah, and I got him, and he was very pleasant and nice, and was able to take my question. But how many times do you see that, where someone puts their phone number on the video for you to call them, and actually answer the phone?
It looked like that one chart indicated that 8 hours of grinding,
Oh, the grinding, yeah.
although that doesn't take into account all the, you know, the prep, the layout, the rinsing,
Yeah.
you know, every other aspect of it.
You know, the other thing this doesn't take into is what is your F number? Because if you're making F4, it's gonna be different than F10. You know, if you got a shallow curve, you're gonna grind that out pretty quick.
And this is just the spherical part of the grind, right?
Right.
This doesn't include your parabolic adjustments.
Right.
Yeah.
And the pitch lap and all the mistakes you make. I made a lot of mistakes that, you know, things like, you know, these come out of a sand mold. I had a tiny grain of sand embedded in the glass. And you know what it came out? When I was in 1,000 grit. 1,000 grit, it came off, went between the mirror and the tool, and put a big groove in it, and I had to start all over again. Then I had one incident where the first pitch I used was contaminated, and that ended up, I had to go back to the start again on that. I had grinding grits, twice this
Get
happened
mixed
on the
up.
grinding grits, they were contaminated. And it put scratches in when I was into fine grinding, there was larger grit in there, mixed in, and I had to go back on that. Don't answer the phone. I remember one time I was grinding the phone, ringing. That's how that chip got in that mirror on the side. I tried to put it in the mirror rack and it dropped. So don't answer the phone. Don't bother me now. Wait until I'm done. I'll call back. But yeah, lots of. The other thing I had is this edge. If you don't keep an eye on this edge, you know, you have to put a bevel on that. If you don't keep an eye on that, that will get extremely sharp, and it'll get so sharp that it chips off. And I had that happen where it got between the glass, the mirror, and the tool. And then that glass, just put a big gouge in there, and then you got to start all over again. There's a lot of different things that may say 8 hours, but until you get the feel of it,
In a perfect world, just that part.
yeah.
If there is a scratch on a mirror, what effect is that on the telescope?
It's more of a psychological effect. Yeah, more psychological than anything else.
With the price of that glass, learning, like, taking 3 or 4 times to do it, that's awfully expensive.
Well,
Well-
you could use the same glass.
Yeah.
You don't have to start with a new one.
You just have to
Just
start
gotta start
grinding
over.
all over.
Just gotta start grinding all over.
Just gotta start over.
I don't know if it's in the.
So really, the only thing you lost is just all your energy and grinding
How can
grits.
you just start all over again? What do you have to do? You
I
need
don't
level,
see
you need to start level again.
No, you already have your curves in it,
Yeah,
but you have to grind that groove out that you put in it.
oh,
So you continue with your tool and your mirror,
yeah,
but you have to go back if you're at 1,000, and let's say you had a chip of glass come in.
Yeah.
A chip of glass is gonna easily go back, you gotta go back to 60. You're not gonna get that out within it. And there's no sense in even trying, because you'll spend forever trying to get that out with 400 or 2. You gotta go back to 60 and grind it all out.
how thin can you get with one of those? I mean, how many tries? you
Yeah.
got?
How many redos do you have in one of those? Yeah.
Quite a bit. If you look at those two mirrors,
Pretty thin.
I had another one which is actually thicker,
Yeah.
because I actually went through all of these problems, and then I changed the focal length on it, because didn't like the focal length.
Because why not?
You know, that's why you gotta make sure you get it right the first time. But, yeah, you could see even on those two, there's a difference in thickness, quite a difference.
What do you do different to get a different focal length?
What's that?
What do you actually do differently to make the focal length? as
If
far
you
as
want
grinding?
if
I
you
know
want a
what you
longer,
curve.
a shorter focal length, then you have to have a deeper curve.
Yeah, I know, I understand
So a
that, but how do
deeper
you make that
curve,
happen?
you hang over more.
Oh.
So you're wearing the center of the mirror against the edge of the tool.
So if you're trying to get a scratch out, what motion are you using?
No,
so
you don't try to
change
get a
the
scratch
depth?
out. You just continue to do the same thing you did before. You don't have to hang over so much. You'll have to continue to test it. You can't do touch-ups. You know, don't try to touch it up.
Right, try to take the
What you
whole
have to
thing
do is, now, if I had a scratch on here, I wouldn't use such a hangover here. I would just go like this, just back and forth, with a short amplitude stroke, center over center, radial stroke. So I don't change it too much. Now, probably what's gonna happen is you're gonna have to put the mirror on the bottom to flatten it out, because you're already at the correct focal length. Now you're grinding the center more,
Yeah.
so you're gonna make it deeper. You're gonna get a shorter focal length, so you'll have to put the mirror on the bottom and the tool on the top and flatten it out. But, you know, same procedure. You can't touch things up.
So as you do your knife edge testing, do you have to keep rotating the mirror as you test it out, or do you just do it in one?
No, you don't have to rotate the mirror. No, because it should be perfect, no matter which way you have it. If it's a perfect sphere, it doesn't matter what orientation you have it. Okay, well, thank you very much.